In this video, I'm going to solve a number of short answer questions. They're good exam problems. The first one is the case where we have two gas phase reactions and we have two isothermal plug flow reactors. So the reactors are identical, and the rate constants for the second order reaction here are the same as the rate constants for this reaction. And then the rate constants for this reaction are the same as the rate constants for this reaction. And the only difference between these two systems is that in the first reactor, 5 moles of A reacts to 1 mole of B, whereas in the second reactor, 1 mole of A reacts to 1 mole of C. And the question is, if we look at the X of the reactor, we look at molar flow rates, so 5 times the molar flow rate of B over molar flow rate of D, and we want to compare that to the molar flow rate of C over the molar flow rate of E. The question is, which one of these is higher? The reason the 5 is here is because we want to compare selectivities. We're comparing now how much A reacts by each of the reactions. And so when 5 moles of A react, we only make 1 mole of B, but 5 times as much of A is used up in this reaction than if the stoichiometry of the second reaction was only 1 mole. And so the question is, which one's greater? Because this is a gas phase reaction, 5 moles of A form 1 mole of B. It means the concentration of A does not decrease as much in the first system as it does in the second system for the same amount of A reacting. Namely, a mole change results in a higher concentration available for reaction in this system. So we have a higher concentration of A for the same amount of A having reacted. And the second order reaction is favored by a higher concentration, so we expect this selectivity to be greater than the selectivity for the second reaction. So the reasoning is that the high Ca favors the second order reaction in reactor 1. In this next problem, we have an isothermal batch reactor, and we're carrying out a first order reaction in the liquid phase, and we have 500 gallons of liquid at the beginning. And we know from previous measurements that it takes 4 hours to get to 90% conversion. While we're running this after an hour, however, a valve is opened by mistake and 500 gallons of water is added into the reactor before the valve is closed again, diluting the concentration of the reactants and products. The question is, what will the total reaction time approximately be to obtain 90% conversion? This is a first order reaction. If we were to look at the mass balance for a first order reaction, batch reactor, we can see it only depends on the number of moles. Because it only depends on the number of moles, we can certainly solve this for the number of moles at any given time is the starting number of moles exponential in time. So the answer is going to be, it's going to take 4 hours again. Diluting it does not change the number of moles reacting per time. The critical aspect is because this is a first order reaction. In this problem, I'm looking at a case of an endothermic reaction in a plug flow reactor. And the problem wants us to plot the equilibrium conversion versus temperature first. And then if we had a feed temperature to the reactor of 320 Kelvin, and we had heat transfer around the plug flow reactor, a jacket at 340 Kelvin, then indicate on this plot regions of possible conversions in temperature that we could obtain in this reactor by changing the feed flow rate, for example. And it says the extremes are, we could run it adiabatically, namely the reaction rate would be so fast that we could not remove very much heat, or we could run it with a very slow feed rate and a high heat transfer, then would add heat in this case. First, on our plot, we want to indicate how conversion changes with temperature. Well, for endothermic reaction, as we increase temperature, we increase equilibrium conversion. So we have something that's going to look like this. This is the equilibrium conversion. As we raise the temperature, we increase equilibrium conversion. And let's label some temperatures. So 340 Kelvin, that's our heat transfer temperature. 320 Kelvin is our feed temperature. So what are the extremes? Well, we can imagine the high heat transfer rate that we can maintain at 340 Kelvin at all conversions up to equilibrium conversion. We're not going to get higher than equilibrium conversion. The other extreme, if it's adiabatic, then as reaction proceeds, the temperature is going to decrease. And to a reasonable approximation, the relation between change in temperature and conversion is approximately linear. That's assuming constant heat capacities. And so we have some line like this. So it's a decreasing temperature. And again, we can only go to equilibrium conversions. This means anywhere in this region it would be possible to operate the reactor depending on the flow rate into the reactor and the rate of reaction. So the last short answer question we'll look at is, suppose you have a reaction carried out in a 1,000-liter batch reactor and you're comparing it to a 1-liter batch reactor. And the question is, for which reactor would you expect conversion to be higher when we have a highly endothermic reaction? So both reactors are insulated, but not well insulated, which means there's significant heat transfer with the surroundings. And both reactors start at a temperature above the surrounding temperature. As reaction proceeds, because they're endothermic reaction, we're going to expect the contents to cool. As the temperature gets below now the surroundings temperature, we're going to have heat transfer into the reactor from the surroundings. For the 1-liter reactor, we have much larger surface area to volume, so we have much larger heat transfer area per reacting volume. So the critical aspect is the surface area for heat transfer over the volume for reaction. So this is larger for the 1-liter reactor, and therefore we expect higher conversion in the 1-liter reactor. And we expect higher conversion because we expect overall the temperature to be higher because of the heat transfer from the surroundings. The other way of looking at it is the reactor does not cool down as much due to the reaction.